Welcome back. In this section, we'll be taking the functions that we discussed in the previous section and graphing transformed versions of those functions. This means graphing versions of the functions after they've been shifted up or down or left or right, after they've been reflected in the x-axis or the y-axis, after they've been stretched vertically or horizontally. These are the sorts of things that we'll do. So part of this is to be able to recognize the kind of transformation that's going on and then to actually carry out the graphing of that transformed function. So here I'm going to start off by, for all of these transformations, talking about how it could be expressed algebraically, and also what that means for the graph as far as visually, what does the transformation look like, and what does it mean for our coordinates? How are we transforming our x and y points when we carry out that transformation? So to start with, a vertical shift. A vertical shift would be something of the form f of x plus k. So if we have a function like the squaring function plus a constant, or the square rooting function plus a constant, that's what I mean by f of x plus k. We have our function and some amount is being added on to that function. That's a vertical shift, and it's a vertical shift of k units upwards. If it was f of x minus k, then it would be a shift of k units downwards. And if we're thinking about what's happening, if we're shifting the graph up or shifting the graph down, we're adjusting the y-coordinate. In particular, if you were shifting it up by k units, you would add k to all the y-coordinates. If you were shifting it down by k units, you would subtract k from all the y-coordinates. So let's do a graph of y equals absolute value of x plus 2. Whenever I do these, I'm going to start out by graphing my basic shape. So in this case, this would be the graph y equals x. And then after that, I'll do the transformed version. So for y equals x, we'll remember that it has the 3 points, 0, 0, 1, 1, and negative 1, 1. And I'm going to just draw my lines. There we go. And then, of course, labeling my points and labeling my graph. So for all of these little mini graphs that I'm doing, I'm going to also be making them well labeled. So that means having the tick marks labeled, the axes labeled, the points labeled, the equation itself labeled. So having everything as well labeled as possible. So there we go. That would be my basic graph for y equals absolute value of x. And for y equals absolute value of x plus 2, what we're going to do now is take that first graph and transform it by shifting it upwards by 2, adding 2 to every y-coordinate. So instead of 0, 0, I'd have 0, 2. Instead of 1, 1, I'd have 1, 3. Instead of negative 1, 1, I'd have negative 1, 3. And then, again, I just need to draw my lines, and then just do a little bit of labeling after this. So my points, I had 1, 3, negative 1, 3. The point 0, 2, I don't have to label that because, again, that's on a tick mark on the y-axis. So I don't need to have that one labeled. I do still need to label my graph itself, though. So there we go. That's my graph of y equals x plus 2. And now the next. This is horizontal shifts. And so shifting rather than up and down, shifting to the left and to the right. One thing that we'll see with all of these transformations is that the horizontal transformations work in sort of the opposite way that we would expect. By that I mean when we were doing a vertical shift where there was a plus k, that meant going upwards by k units. And that was Pretty intuitive. That's kind of what you would expect it to be, that plus k means going up by k. But we'll see that with horizontal shifts, things are actually the opposite. If you see f of x plus h, you might be thinking about that being a shift to the right, or going to the right by h units, but instead it's going to be the opposite. It's a shift of going to the left by h units. F of x minus h, that would be what you'd think might be a shift to the left, but it actually is a shift to the right. Also, not just in what does the transformation do is the opposite of what you'd expect, but the actual arithmetic that's being done with our coordinates is the opposite as what you would expect. So by that I mean here, when you were thinking of f of x plus k, we added k to all the y coordinates, and that was, again, what you would expect that you would do. However, for f of x minus h, instead of subtracting h from all the x coordinates, you're instead going to be adding h to all the x coordinates. Now, one thing to be careful about here is interpreting this little symbol that I've written, this f of x minus h. This doesn't mean that we're taking a function and subtracting some constant from it. Rather, what it means is that the x's inside the function are all having that value subtracted from it. So, for example, if f of x were the squaring function, and you wanted to say what is f of x minus 3, that would be the function where x is having 3 subtracted from it, and then it's being put into the squaring function. That's what I mean by f of x minus 3, as opposed to the vertical shift, f of x minus 3, where 3 is being subtracted from the entire function. That's for a vertical shift. Here, 3 is being subtracted just from the x. That's a horizontal shift. This would be a shift to the right by 3 units. This would be a shift downward by 3 units. So that's one thing that we'll need to be able to do, to be able to distinguish between these two kinds of transformations. Which one is a transformation in the y direction, which one is a transformation in the x direction. An easy way to sort of keep this straight is the fact that when we're talking about things that are in the y direction, it's amounts that are being added to, subtracted from, or multiplied by the entire function. So this minus 3, that's being subtracted from the entire function. That's what makes this something that's vertical. Something that's horizontal are amounts that are added to, subtracted from, or multiplied by the x values. So here it's the x that's being having 3 subtracted from it. That's why this would be a horizontal transformation. So something like this, y equals x minus 1 squared. This is the squaring function, but 1 is being subtracted from the x's. So that means that we're going to start by graphing y equals x squared, and then we're going to transform it, and we're going to transform it by shifting it to the right by 1 unit. And when we do that, we're going to take our original function, y equals x squared, and we're going to add 1 to every x coordinate. So I'm going to begin the same way that I always do, starting by graphing my basic shape. In this case, the parabola y equals x squared. Plotting my points and labeling them. There we go. And then, of course, labeling my graph itself. I know I'm going to say this about 1,000,000 times before the end of the year, but I'll say it now again, that remember that when you're graphing anything, I want to see the axes labeled with x and y. I want to see numbered tick marks on the x and y axis. I want to see your points labeled. I want to see the equation labeled. So this, what I've given you here, this would be a nice well-labeled graph of y equals x squared. Now for y equals x minus 1 squared, this is where we're going to take our graph and transform it by shifting it 1 unit to the right, And we do that by adding 1 to every x coordinate. So negative 1, 1. I was a little hasty, not really writing carefully. There we go. Negative 1, 1. When I shift that to the right, that goes to 0, 1. 0, 0. Shifting it to the right by 1, that gets me to 1, 0. 1, 1. Shifting that 1 to the right gets me to the point 2, 1. I'll just label my points, label my graph, and there we go. We've got our well-labeled graph of y equals x minus 1 squared. So far we've seen two types of transformations. We have vertical transformations when amounts are being added or subtracted to the entire function. We've also got horizontal transformations, horizontal shifts, amounts that are being subtracted or added from the x values. And then now we're going to talk about flips and stretches. I'm going to start with vertical stretches here and vertical compressions, then we'll do horizontal. So first, for the definition of a vertical stretch, what does it look like algebraically? This would be something where the entire function is being multiplied by some constant. So by that I mean something like if the function was x squared, having a constant multiplying by the entire function. So it's not just the x that's being multiplied by 5, it's x squared being multiplied by 5. Or something like the square rooting function being multiplied by a constant. That would be something that would be a vertical stretch or vertical compression. So when we have our function being multiplied by a constant, and here we're imagining that this constant is something positive for now. We'll talk about what if the constant is negative. But if we've got a constant that's positive and it's multiplying by our entire function, that represents a vertical stretch by a factor of a. And we carry that out just by multiplying all the y values by that factor of a. So we take all of our y values and multiply by a, and that carries out our vertical stretch or our vertical compression. Depending on how big a is, that's why we'll call it a vertical stretch or a vertical compression. Because, as you know, we were going to take each y coordinate and multiply it by a. So if a is some number that's larger than 1, you're going to be stretching your graph out vertically. It'll be getting taller than the original graph. So, for example, 2x squared should be twice as tall compared to x squared. On the other hand, you might have a value that's between 0 and 1, in which case you're not really stretching it anymore, you're compressing it. You're multiplying by a number that's less than 1. So something like a half times x squared, that would be half as tall as the original function y equals x squared would be. So you might say, instead of calling it a vertical stretch, you could say it's a vertical compression. It's a compression by a factor of 2 because you're twice as small as the original function y equals x squared. So the thing to remember here, of course, as always, vertical transformations are things that are done to the entire function and they affect the y coordinate. So to take a look at this next example, y equals 2x cubed, I can see that it's not just the x that's being multiplied by 2, it's x cubed that's being multiplied by 2. So if we're thinking about our function, the cubing function, that whole function is being multiplied by 2, which means we're going to be vertically stretched by a factor of 2. We'll be 2 times taller than the original graph of y equals x cubed. Now, of course, same thing as always, I begin by first drawing my basic shape. And for y equals x cubed, it has the 3 good points, 1, 1, 0, 0, and negative 1, negative 1. And now to carry out the transformation, that vertical stretch, by a factor of 2, I'm going to take all of my y-coordinates and multiply them by 2. So 1, 1, when you multiply the y-coordinate by 2, you get the point 1, 2. Negative 1, negative 1, when you multiply the y-coordinate by 2, you get negative 1, negative 2. And 0, 0 is going to stay where it is. Anybody who has a y-coordinate of 0, multiply it by 2, the y-coordinate will still be 0. So that means anybody on the x-axis will stay where it is. So that point 0, 0 stays where it is. And you can see that we've got now a narrower, taller version of that cubic graph. And as always, horizontal things are done in the opposite way that we did them for vertical stretches, or vertical shifts, or vertical anything. So first off, as opposed to the entire function being multiplied by a constant, it's just the x that's being multiplied by a constant. So for example, if I'm looking at the square rooting function, something like 2 square root of x, this would be the entire function being multiplied by a constant. That would be a vertical stretch. As opposed to the square rooting function where just the x is multiplied by 2, in which case that would be something that's horizontal. Now, a couple of things about these horizontal compressions and horizontal stretches. The first would be the how we do it. If you're flashing back to a couple of slides ago, for the vertical stretch, we're multiplying every y-coordinate by that number a. And so, as you know, when we do horizontal things, we do the opposite of what we might do for the vertical. So if you are, for a vertical stretch, multiplying every y-coordinate by a, then that means in the horizontal stretching, instead of multiplying every x by a, you'll be dividing every x-coordinate by a. And so what that means for us then is that if you have a large value for a, and you're dividing every x by that larger value, you're going to be making your x value smaller. That's going to then compress your graph in. So for example, something like y equals square root of 2x, that would be 2 times narrower. So whatever the original graph might look like, y equals root of 2x would be 2 times narrower. If you're looking at a value between 0 and 1, this would do the opposite. This would stretch your graph out and make it wider. So for something like here, I've got y equals absolute of 1/2 x. You're going to be dividing every x coordinate by a half. That's the same thing as multiplying every x coordinate by 2. So your graph is going to get 2 times wider than the original graph would have been. So let's do this one, the square root of 2x. So again, this is something that is a horizontal compression because the 2 is not being multiplied by the entire function. It's multiplied only onto the x. So that means that it's going to affect the horizontal direction, the x-coordinates. So first I'll start with my basic graph, y equals root of x. And so we know the 3 good points for y equals square root of x are 0, 0, 1, 1, and 4, 2. For our follow-up graph here, y equals root of 2x, what we're going to be doing is taking every x-coordinate from the original graph, and we're going to be dividing it by 2. So every x-coordinate divided by 2, we have 0, 0. That x-coordinate, dividing it by 2, it still stays as a 0. But for the point 1, 1, if we divide the x-coordinate by 2, we'll get the x-coordinate of a half. Y value would still be 1. And finally, we have the point 4, 2. If we were to divide its x-coordinate by 2, we would have the point 2, 2. Just going to label those points. And there we go. That's my graph of square root of 2x. So we've taken the original graph that we had of y equals root of x, and we've compressed it in horizontally by a factor of 2. It's 2 times narrower than it originally was. Finally, if we're talking about the last kind of transformation, these are vertical flips and horizontal flips, which, as it turns out, they're really just a little extra thing that could be considered part of the vertical and horizontal stretches. So remember that when we had back in the vertical stretches, we were saying that the number that we were multiplying the function by was always going to be some sort of positive. And I said that we would address, well, what happens if you're multiplying by something that's negative? And as it turns out, multiplying by a negative gives us the effect of a vertical flip. So if you were to take your function f of x and multiply it by -1, negative of f of x, that's multiplying every y-coordinate by -1. So that means that any points that are above the x-axis will now be below, and any points that were below will now be above. So, in other words, you've taken your function and the graph of it, and you've flipped it in the x-axis. You've vertically flipped it. As I point out here, this can be done at the same point as a vertical stretch or a vertical compression. So if I were to look at, for example, the squaring function y equals x squared and multiply it by -2, it would be stretched by a factor of 2 and also flipped in the x-axis. And I can do both things at the same time, because what I'd be doing here would be multiplying my y-coordinates all by -2. So that's what we'll do here. We're going to graph y equals -3x squared, which means we're going to start with our basic shape, our parabola, y equals x squared. Make that look a little less lumpy. There we go. And there's my graph of y equals x squared, passing through its 3 good points, -1, 1, 0, 0, and 1, 1. And then now for y equals -3x squared, I'm going to do the stretch and the flip all at the same time by multiplying every y-coordinate by -3. So that means that the point 1, 1, multiplying its y-coordinate by -3, gets me 1, -3. 0, 0, its y-coordinate is 0, multiply it by anything and it stays as 0. -1, 1, multiply that y-coordinate by -3, you get the point -1, -3. And then there we go. We've got ourselves our graph of y is equal to -3x squared. It's 3 times taller than the original parabola, and it's also been reflected in the x-axis. And then finally, the last transformation, that would be horizontal flips, reflecting things in the y-axis. And so not a surprise here, when it was the entire function having a negative applied to it, that was reflecting things in the x-axis. When it's just the x's with a negative applied to them, that's a reflection in the y-axis. Of course, same thing as before, you can do a reflection in the y-axis at the same time you're doing a horizontal stretch or a compression, because in this case you would be dividing every x by, in this case, -1, and that would be doing your flip. But if you had something like, for example, root of -2x, you would have a flip happening, and you would also be 2 times as narrow as the original function, and you would do both by dividing the x coordinates all by -2. So something like this, we've got our square rooting function, and it's y equals square root of -1/3 x. So the negative, that's going to be doing a reflection in the y-axis. The square rooting function, we know it originally points off to the right. So for the negative, that will make it now point off to the left. The other part that we have, that -1/3, we're going to be dividing every x coordinate by -1/3, which is the same thing as multiplying every x coordinate by -3. So in addition to the reflection, it's also going to be 3 times larger, or 3 times wider, than the original graph. So the original graph, let's plot it. For the graph of y equals root of x, we know it's nice 3 points, 4, 2, 1, 1, and 0, 0. And now for y equals -1/3 x inside the square root, like I said, we're going to take every x coordinate and divide it by -1/3. So the point 0, 0, take that x coordinate and divide by -1/3, it's still 0. But the next point, 1, 1, if you divide that x coordinate by -1/3, that's the same thing as taking the x coordinate and multiplying it by -3. That gives you the point -3, 1. And then same thing with the last point there, 4, 2. Take the x coordinate and divide by -1/3. That's the same thing as taking the x coordinate and multiplying by -3. That brings me to -12, 2. And there we go. We have our graph of y equals root of 1/3, -1/3 x. And you can see it's 3 times wider than the original square root graph, and it's also been reflected in the y-axis.